last week. I am Ethan Smith. I'm a field service rep, service advisor, DSG, whatever you want to call me, for GA Larson. I'm based out of the Salt Lake City, Utah branch. We also have Keith Wilbur on the Wildhaber, however you pronounce his name. I'll let him introduce himself.
Hello, everyone. Welcome to the meeting.
He's our newest rep, and he's based out of Denver, Colorado. So this class is a continuation of the electrical theory 1 class, which we had last Wednesday. So we're gonna get back into it here. Before we get going, does anyone have any questions regarding what we covered last week or anything they wanted to clarify? And you guys feel free to unmute yourselves. We're going to try and keep this as open forum as possible. If you prefer, you can put stuff into the chat. Keith's going to be monitoring that, and he'll let me know if I need to stop and answer a question there as well. Okay. Well, we're going to go ahead and jump back into this presentation. We've got a couple things that we didn't do last week that we're going to catch up on, and then we'll keep going here. But just to review, don't do that. So we were talking last week, we ended up talking about motors and capacitors, and kind of, by the way, there's all of our phone numbers if you guys need those. This is a good screen to take a picture of. I can also send you those if you email me after class. But we kind of played around with this motor a lot last week. Talked about how to identify speeds and different things that we could do with this motor. And then we got into capacitors. Which is just these two metal plates separated by a dielectric. We pulled one apart so we could see the inside of that thing. And then we talked about applying those things to motors and making sure that we get the right capacitor for the right motor. So we went over this chart here where we played around with some capacitors on the same motor to get different results. And we can see that we kind of hit our sweet spot with that 4 microfarad capacitor there. One thing I didn't cover that I wanted to cover, and I'm going to pop out of this really quick here, is what happens when we have alternate capacitors. Stop this, or we need to build capacitors. So how capacitors combine and work together. So we've got the Ubiquitous multi-tap capacitor. Mine's transparent just so you guys can see what's inside one of these guys. And it's really just a giant spool of metal foil with dielectric in them. And each one of these taps on the top corresponds to a different point in that spool. You can kind of see that they all land at different points in there. So we have multiple capacitors. So a couple things about capacitors. This is a multi-tap. Obviously, we've got single taps where we're just using two taps on it, and it's just a single capacitor value. This is the one we pulled apart last week. We've got one hooked up to our motor here. They all have different ratings. So this is a 5 microfarad. The one we pulled apart was, I think, a 3. Yep. But if you don't know what a capacitor is, because heaven knows that these things always have labels that are clear and easy to read, right? It is possible to figure out what a capacitor is. You just need your electrical meter that has a capacitor test. So this little symbol that we see right here, and I'll pull that up here and hope that my camera will focus in that tight. Come on. There we go. So this little symbol right there with the 2 white lines, one of them's curved and one of them's straight, that is the electrical symbol for a capacitor. And I can turn the light on here. Okay. And we can simply take our meter leads, and my terminal that's common to all these capacitors is in the middle here. And then I can touch each one of these and it will give me my capacitance value. So that's a 2.5 microfarad capacitor between those 2 points. 5 microfarads there. 6 microfarads there. If we keep spinning around here, we've got a 24 and a 20 and a 10. Okay. So who remembers how resistors interact? If you put 2 resistors in series, what happens to the resistance?
You add them together.
Yeah, they add together. So it's just R1 plus R2. Capacitors behave a little differently. They kind of behave a little bit like resistors, but in reverse. So resistors, when they're in series, add. When they're in parallel, who remembers what happens to them? What happens to your total circuit resistance when we put resistors in parallel with each other?
You have to use a formula. I can't remember, but it's like lesser.
Yeah, the resistance goes down. So I've got a couple capacitors here that we can play with, and I've got some jumper wires. Let's fiddle with this a little bit. So we're going to put a couple capacitors in series here. So I've got this capacitor here, which is 5 microfarads, and we're going to jump it to, I believe that it was this terminal right here, one of my whites that was also 5. So that's 5. And we're going to put these 2 capacitors in series. And then I'm going to test from one end of that circuit to the other. And what you notice is the capacitance actually goes down. So the capacitors actually act exactly the opposite of resistors. So capacitive loads are inversely proportional. So when you put them in series, they actually result in a lower capacity. However, if you put them in parallel to each other, so we'll add another jumper here. So I'll tie the 2 other sides of the capacitor together. So now this is in parallel. So we've got 2 5 microfarad capacitors in parallel. This is when they add. So I'm going to go across it there. And I've got 10.5 microfarads at that point. So in parallel, capacitors are additive. And in series, they're inversely proportional. Okay. So you guys noticed that when we had the 2 5s in series, it went down to 2.5. And when we had them in parallel, they went up to 10. Okay, so it follows those same rules, just in reverse. So this being a multi-tap capacitor, the way these are meant to be used is if you say need a 25 microfarad capacitor. There wasn't a 25 microfarad as I recall here. We had, no, there's a 25 there. So let's say we need a 30. There's definitely not a 30 capacitor in here. So I've got 25 there and I've got 5 here. What I can do is, because this port is tied to both of these, I can make it parallel circuit just by putting this jumper wire between the 2 sides. And so now if I test between these 2 and actually get my probes on, come on. It's not happy with me. Oh, I can't test that way. I got to test this way. I should get a 30 microfarad reading, which I do. Okay, and I can do this as many times as I want. That's why these things have so many blinking taps on them. I can get my 25, my 5, my 15, or whatever this one is. And I can go to any point on this circuit, and it'll add up all those capacitors that I've got in parallel. So this can come in handy out in the field. You're out on that thing, you notice we're getting the same reading at all our different points here, 49.5, because they're in parallel. So this come in handy in the field. You need a 7.5 microfarad capacitor. All you've got is a 5 and a 2.5. You can make your 7.5 capacitor. I got to the point in my service career where these multi-tap capacitors were the only thing I kept on my truck, just because they saved me so much time on service calls.
Is that recommended?
Which isn't to say that I never had these capacitors. If I was doing a motor replacement, I would generally, when I purchased the motor, I would purchase a capacitor like this to go with that motor. But I had a very limited supply of these things on my truck. I think I carried them for my rescue motors, but for general purpose, I carried these big multi-tap capacitors for the ACs. And they also have smaller versions. So this is a little smaller one, and then they actually have an even smaller version than this that's about this big that has 3 sizes. But capacitors come in all shapes and sizes and forms and application and insulation values. The things we have to be careful of is we need to be, when we're replacing capacitors, we need to be plus or minus 5% of our capacitance rating. No more, no less than that. And we need to make sure that we match that voltage rating that's on the capacitor. Okay. And that voltage rating needs to be matched to our motors. Okay. So those are the 2 things. We can always go up on the voltage rating on the capacitor, but we can never go under the voltage rating of your motor or your previous capacitor. It refers to the insulation value. So we can always have extra insulation. That's not a problem. But if we don't have enough insulation, it will result in a premature failure of the capacitor and probably the motor as well. So any questions about capacitors, guys?
Would you recommend leaving them in that when you put them in?
Say that again?
When you left, would you recommend leaving them jumpered together? Or is that just a short term?
That's meant to be a permanent solution like this. I don't really have a problem if you've got to gang multiple of these guys together. It works the same way. It's just a bigger solution there, ganging 2 of those together. You know, I'd prefer to have a capacitor of the right size or one of these in an air conditioner versus trying to find a place to mount 2 of those. But sometimes it's Friday night and the stores are closed, and this is what you got to do to get them running. So you could certainly take those jumpers there, and I wouldn't have any problems with longevity as long as you're matching your capacitance and your insulation value with those guys. I've lost my jumpers for some reason, but we can do the same thing with these. So this is a 40 microfarad, 440 volt, and this is a 5 microfarad, 440 volt. We can tie these in parallel if we needed a 45 microfarad capacitor. And we get our 45 microfarads on our meter anywhere we go. Cool.
Yeah, that's a cool thing there.
Cool little trick. Conversely, if I needed a 35 or something a little under 45, I can put these 2 things in series and I'd get a different rating. Okay. So even though this is a 40 microfarad capacitor, I'm limited by this thing, which is a 5. And so it actually gives me a lower capacitance overall. So I'm at 4.5 there, approximately. So kind of tricky how they can combine, but useful as long as you know. But generally it's tough to find room in the air conditioner to have very big, lots of real estate devoted to capacitors. So, but it can come in handy and get you out of a bind. Other questions about capacitors, guys? Get this guy turned off here. Okay. So let's hop back into the presentation here. Okay. There's our capacitor worksheet. So what do we use capacitors for, guys? I mean, previously we had one wired up to our motor. What's that capacitor used for on this motor?
Resistance and torque
Say that again?
for torque.
Yeah, we can use them for starting torque. The motor we were working with last week was a permanent split capacitor, means the capacitor is always in circuit with the start winding. What are we using it for in that case?
Efficiency, or to help it get in phase.
Yeah, helps us with our efficiency. And we can kind of see that with here, we're balancing running torque versus our efficiency. In this example that we showed where we had the multiple different ones, we had a little lower overall torque with the 3 microfarad capacitor versus the 4 microfarad capacitor. But we do lose a little bit of efficiency when we go up to that 4, but that torque was more important in this case, and so that's what we go with.
And is that because it's adding like a sort of a third phase, right?
A second phase, yeah.
Okay.
In this case, this is a 115 volt motor, so it's got a single phase of power, and then we're creating a second phase of power by offsetting that second phase with a capacitor. So we get that extra starting torque there, and we lose a little bit in efficiency. So we're kind of balancing those two, and that's kind of our sweet spot, because when we went to a 5, we didn't really gain anything on our torque, but we lost a lot of efficiency there. Okay, so that would be a permanent split capacitor. The other thing we mentioned was we can use capacitors to help start. So we talked about the centrifugal motors and relays that helped start our capacitors. So we can actually combine those. Anybody ever seen this little chunk of wiring somewhere before? Where might you see this? This is a capacitor start and run system. I guarantee you that you have. So this is very common in air conditioners. This could be an air conditioning compressor. You've got your run capacitor that we're always used to seeing, but a lot of times you'll see a start assist capacitor on there as well. And it comes with a little box attached to it that we call the start relay. So these start relays are kind of fun in that what they are is this start relay. This little symbol right here is the coil of the relay. So that start relay, what you'll notice is the voltage rating on that start relay is very close or similar to the voltage rating on your capacitor. So you'll have a start relay that'll have a 330 volt pickup voltage. And the reason that is they're using the back EMF of that motor to pull that start relay in once the motor is spinning. Okay. And so what we're doing is we've got a capacitor in series with the start winding, just like our PSC motor, for efficiency. And then we've got a start capacitor in series or in parallel with the start winding for starting torque. So now we don't necessarily have to balance efficiency versus torque, because we can give it a whole bunch of torque until it starts moving and then drop it out and then have another capacitor there that's just for efficiency. So once this motor starts spinning and generating that back EMF that we talked about last week with the motor, it's going to engage this relay, which will break the circuit between the start capacitor and the start winding. Okay, that essentially drops that capacitor out of circuit and allows the compressor to continue running with just the run capacitor in circuit. So we go back to this chart where instead of just running with a single run capacitor all the time, we conceivably could put a 5 microfarad capacitor in there as a start capacitor and use that to get our extra starting torque. But once the motor's spinning, drop that capacitor out and run it on a 3 microfarad capacitor for efficiency. Does that make sense? Any questions about this?
No.
So this mystifies a lot of guys out in the field because you got this magic black box. Well, that's all that magic black box is it's just a coil and a set of contacts. The trick is these are normally closed contacts. So when the motor's disengaged, that winding isn't energized, and so these are in circuit with the start capacitor. Once the motor starts to spin and we get back EMF, those contacts are going to open up and drop that start capacitor out. That's why occasionally you'll see start capacitors blow up when you have a locked compressor, because what's happening there is we're keeping that start capacitor engaged, trying to get that motor to spin, but it never starts spinning. These start capacitors are generally not meant to be in circuit for more than a second or two. And so they start to break down when they're constantly engaged on something like a locked rotor compressor. So occasionally you'll see the little relief port on those things blow off, and the inside of your compressor or your electrical cavity will be covered in this black or white goo that's blown out of that capacitor. So. And then of course we've just got our standard run capacitor. So this run capacitor would be doing double duty as a starting torque capacitor and an efficiency capacitor, whereas this one we can use a big capacitor to give it a big hit of torque on startup, and then have a run capacitor for efficiency once it's spinning. Okay. Any questions, guys? Cool. So we're going to talk a lot about switches here. So switches are how we control all of our electrical loads, and that's kind of how our industry revolves around us. And come on, we throw around these names quite a bit, and so this is a good thing to be taking notes on, guys, because I'm going to quiz you later. So we have things called throws and things called poles. So we'll start with the simple one. This is a single pole, single throw relay. So this would be a relay that has one armature. That's the number of poles that it has. And it has only an open or a closed position. So it's only got one set of contacts. So this would be a single pole, single throw switch. Couple different ways that it can be pictured on your wiring diagrams. This becomes important later. Okay. Now, a single pole, single throw normally closed is going to look a little different. It's going to look like this. We get the line through those two contacts, or we get the closed switch position. Okay. So we've got lots of different ways of looking at switches here. So this is no longer single pole, single throw. What do you guys think this one is?
Double pull, single throw.
Okay. Anyone agree with him? Anyone disagree with him?
Agree.
Okay, it is a single pole, but it is, or actually it's not a single pole. Whoa, sorry about that. That is a double pole, single throw. So it has two armatures, but only one closed position. It can either be open or closed, but it doesn't have any extra sets of positions. So double pole, single throw. have the two contacts. This is another way you'll see this. You see this on peanut relays, things like that, quite a bit. This would be a normally open version. Okay. This goes through all sorts of permutations. Okay, so we've got all our single poles here, single pole, single throw. So this would be a single pole, single throw, and then we can add another level of complexity in here that would be a single break. And this would be a single pole, single throw, double break, because we're breaking it at 2 points. So this would be like a contactor. This would be more of a switch. Okay. After that, we can get into double throws. So this would be a single pole double throw because it has two closed positions. So this one has either, you're either normally open down here and normally closed up here, or you can be normally closed down here, normally open up here. We can do that as a double break solution as well. We can go into double pole, single throw, single break, double pole, single throw, double break, double pole, double throw, where we have two closed positions, single break, or we could go all the way up to that double pole, double throw, double break. So they just get more complicated as we go up. So this would be your double pole, single throw, normally closed, because its unenergized position is in that closed state. Okay, so I'm going to throw this one out here, guys. What do you think this is?
Single pole, double throw.
This is a single pole double throw. So we've got that normally closed position up here, normally open down here, normally closed up here, normally open down here, and the same thing down here. It's just flipped over. Good go. It's got one normally closed and one normally open on a single pole double throw. Okay, we can keep going here. What's this one, guys?
Double pole, double throw.
So
You muted yourself.
yeah, I did. So yeah, that is the double pole double throw. Okay. What about these guys?
Triple pole, single throw.
So that one's a triple pole single throw. It's a little unique in that it has this little guy up here. What about this one down here? Any thoughts on this one? Down in the bottom left?
It looks like a triple pole, single throw still, but the space is strange.
So it's a little weird. This one's actually a triple pole double throw because you can be in this position or you could be thrown all the way over here in this position. Okay. What about this one, guys? Bottom right.
Single pole, double throw.
That's correct. So this one up in the left is a little tricky because it has this little extra armature up here. This is a manual switch. So this would be how a disconnect would be pictured on a wiring diagram. Got that little armature. Okay, so troubleshooting switches. We kind of talked about this a little bit last week, but a closed switch when it's under power, what kind of voltage reading should you see across a closed switch?
0.
Should be 0 volts because a closed switch, when it's energized, is just a piece of wire. It's a conductor at that point. You don't get any voltage across the switch until you open it. Okay. Other troubleshooting steps. Let's pull out my power supply here. and switch cameras. Okay, so I've got a little relay here. Let me get my power supply plugged in. I've got my 24-volt source here. I've got the wrong set of leads on this guy. Sorry, bear with me, guys. Grab my jumpers here. So this particular relay here, and we'll come down a little closer on it, is what, guys? What do you think this one is? We see this one all over the place. My two terminals up here are my coil voltage. And then I've got two sets of contacts here. I have my common here on the right. And if I go to this one, it's supposed to be normally open. If I go to this one, it should be normally closed. No, backwards. That's normally closed. That's normally open. I got the same thing. I've got another set of contacts here. So common, normally open, normally closed. So what does that make this switch, guys?
Single pole, double throw.
It is a single pole. Oh, that's not a single pole. Excuse me.
Yeah, double pole.
Double pole, double throw. Okay, and we can test this. We'll pull the meter over here. I've got it set to read resistance. So if I go to my common terminal, I should have 0 ohms right there. So yep, 0.2, that's almost nothing. That's my normally closed switch. And over here, I should have infinite or OL. So we can see that. Same thing here, infinite, or excuse me, this one's the normally closed, so that's no resistance, and OL on this one, which is infinite. Okay. Now, if I were to power this switch, we'll notice that my resistances across the switch have changed. Now I have an open line there, and I'm closed here, because now we've energized that normally open set of contacts. So now it's energized, it's normally closed. Same thing on this one. We've got open line here and normally closed there. Okay. So we can take this one step further. So we'll de-energize that relay. And let's put our power right here. Okay. So I'm going to turn my power source back on. I'm now feeding power into this set of terminals right here. So let me scoot around here and get my meter on there. Which one of these should I be reading a voltage drop through? The normally closed or the normally open? Where should I be reading a voltage drop?
Normally closed.
Okay. What do we read? What do we read for voltage across closed switches, guys?
Nothing.
Okay. I got no voltage. No, helps if I put it on voltage. Okay. I've got no voltage drop there. But if I go to this one, which is normally open, now I don't have anything connected to this, so I'd have to go to a common. So if I go common, to that side, I got nothing. But here I've got voltage because I'm not connected. But if I go, come on, there to common, yep. But here I've got nothing, okay, because I'm not connected to anything on this side. So there I've got no voltage because it's closed. If I go to neutral, I've got 26 volts there. If I go to the other side of my switch, I also have 26 volts because we've got a continuous path here to here. Okay, that makes sense? Clear as mud? Okay, so there's two ways you can test switches. You can test them voltage-wise, or you can disconnect the loads off the switches and test with resistance. So we have our de-energized state. We've got no resistance on our normally closed. Once I energize that circuit, now I go to an open line there. Same thing here. Energized, I'm closed between those two leads. De-energized, I'm open. If I can keep my meter leads on them. Energized, de-energized. Cool? So everybody knows how to diagnose a switch now, right? So when they're energized, we have what voltage drop across them?
Well, if it's
Zero on
on,
the closed one.
Yeah, when we've got an energized switch, it has 0 voltage drop across it. And when we have a de-energized switch, it's got whatever the voltage supplied drop across it. So closed switches, 0 voltage, open switches, source voltage. Any questions, guys? Okay. I know I was kind of crammed down in there on that meter. All right. So lots of kind of different switches we've got here, guys. So we've got a lot of different names for switches. One of them is relay. So this is some kind of a switch that's activated by a solenoid coil. That's what we were just looking at. So these can be peanut relays. They can be fan relays. This one's, I'm gonna go back to this one. This one is actually a quad pole double throw. So we've got 4 sets of poles, but only 2 positions. Okay, this would be a single pole double throw because we have 1 set of contacts instead of 2 like the one I was just showing you. This one's another double pole double throw peanut relay. We've got relays on boards. These big black boxes you typically see there are relays. This is a defrost board out of a unit. Okay, but they all operate the same. We use a magnetic coil to operate a switch. Okay, so we've got 2 components in there, the solenoid coil and the switches. So we talked about how to troubleshoot switches. Let's talk about how to troubleshoot the coil now. Okay, so coils, when they're energized, are resistive loads. And so they should behave a little differently. Oh, silly thing here. Grab my other camera here. So back to our relay and our meter. So coils, when they're energized, we mentioned that my coil contacts are down here. And if we look at this really closely, you can kind of see right down this wire, you'll see a little wire track that comes down to this solenoid pack that's down here. Turn this light off, see if we can see it any better. but you can see where this post is. There's a little wire inside there, and that tracks around down into the pack. Again, we've got another wire on this side that tracks down into this pack. And this is just a big coil of wire around a iron core that is operating these switches. So a couple different ways we can diagnose a solenoid. We know it's energized if it's getting power, so that one's pretty easy. We would just test a voltage across these two leads. But you can also test the solenoid coil by taking a resistance reading through it. Sometimes you know what that resistance reading is going to be. This one we do not. It just gives us our designation. It's a 24-volt coil, and it gives us our amperage ratings and our voltages here, but it doesn't give us a resistance reading. But we know it's a coil of wire. We should have some resistance through it. So this gives us a place where we can diagnose. So if we put our meter leads on this thing, we'll notice we have 18 ohms of resistance through it. Now, if we were to come up to this coil and we were to get on it and it gave us an OL, we would know that that coil is broken somewhere because we should have an electrical path through a coil of wire. Okay. So we don't know if this 18 ohms is correct or not, but we do know that it does have a coil there. Conversely, if you were to get onto a coil and you were to notice that it gave you almost no resistance, or if you were to take a coil to a ground position, so this is a grounding terminal right here, we would know if that had continuity there and a resistance reading, we would know that this coil in here has shorted to ground. Typically, you're going to see popped fuses if you see that kind of thing. But this one, we've got just our coil resistance right there, 18 ohms. So we know that we have a coil. We know it's intact. We've got no continuity to ground. Okay, and it's not OL and it's not a dead short. So we know that this coil is probably okay. Okay. So most 24-volt coils on residential equipment are going to read between 10 and 20 ohms, depending on how big of a contactor they are. That coil is going to change size. Rooftop units, typically their contactors are around 15 ohms. Okay, but that's kind of how we're going to test coils. So we can test the contacts really easily, just open or closed, voltage across them, or we can ohm across them. Coils are the same thing. Coil under load is going to have a voltage drop across it because it is a resistive load. And when it's unloaded, we want to take a resistance reading through it. Now you'll notice that there's no wires connected to this. Now, conceivably, if I had wires connected to my coil and I tried to take a resistance reading through it, even if my coil was open, okay, it could find an electrical path back through the rest of the electrical circuit and get continuity somewhere else. And that's a little easier to see on the wiring diagrams later. But this is why when we're testing resistance through a device, we have to make sure that at least one side of that device is disconnected from any wiring. That way it can't find an alternate path around the circuit and give us a false reading. So when you're testing resistance, always make sure to unplug or unload the wires off of one side of your device or switch or coil or whatever it is. Any questions, guys? Okay. Let's go back to this presentation here. So we've got our two components, solenoid and a switch. We talked about troubleshooting. So contactors. Contactors are the same thing as a relay. Generally, you just have higher amperage contacts. So we could even call that little relay there as a contactor. But typically, we're talking about stuff like this that has multiple high amperage ratings, all the way up to big mag starters. Okay, it's just a big contactor, guys. That, you know, whereas we may have a 10 amp max in this, we may have a 60 amp max on something like this, and we may have a 200 amp max on something like this. The components change places a little bit. So on this contactor, we've got our coil terminals here. On this one, they're back here. And on this one, they're actually in the middle right here. So those are our coil contactors. We may have different voltages. This is a 24 volt coil. This is a 24 volt coil. We can see on this one, it's actually 110 volt coil. So it kind of depends on your application, but all they really are, guys, is big magnetically driven switches. That's what a contactor is. That's what a relay is. Contactors sometimes have different terminal designations, especially if they're three-phase. You'll have L1, L2, and L3 on one side, and then you'll have T1, T2, and T3 on the other side. So we use this a lot. That's usually labeled on the contactor. It's a little tough to see in this picture back here, but if my photo was a little higher resolution, you'll notice that these are labeled L1, L2, L3, and T1, T2, T3 back here. Okay. Same thing. We've got a coil and we got a set of switches on them, guys. Any questions about diagnosing contactors, relays, switches, anything like that? Okay. So let's dive into heaters. Where do we see heaters in electrical circuits, guys?
Strip heaters, I guess, are resistor.
Yeah, strip heater is a resistor. Bronson, you mentioned 6 to 9 ohms. What are you referring to?
He was just talking about the Ohm's law, right? I was kind of confused by that. Was he just asking?
Gotcha. He's answering Keith's question. I'm sorry, that popped up on my screen.
Oh, no worries.
Does that make sense, Bronson?
The question?
Yeah.
That he asked? I understood it.
Okay, cool.
You see them in
Gotcha.
crank heaters?
Yeah, straight resistance heaters would be one place where we'd see heaters. What other kinds of heaters do we see?
Crankcase heaters.
Crankcase heaters, okay? So keeping the crankcases of the compressors above ambient. Any others? What about a heater as a control? Do you ever see heaters as controls?
Thermostats, kind of.
Yeah, there is a heater in a conventional thermostat. The old analog thermostats had heaters in them. They were the heat anticipators. So they were that little piece of wire that went around the perimeter, had a little armature that you had to adjust. That was the heat anticipator. It was a little tiny piece of nichrome wire that was a heater. Where else might we see heaters, guys? We got that one already.
Safety switches.
Safety switches. Okay. Water heating, crankcase heaters. What about control panel heaters? Anybody ever encountered a control panel heater? Okay. You'll sometimes see these in super cold climates where you've got to keep the electrical system above a certain temperature in order for it to keep running. So they'll actually have little resistance heaters in the control panels. Okay. We talked about heat anticipators. What about time delay circuits? Anybody ever seen a heater in a time delay circuit?
I've read about them, never really seen one or troubleshooted it.
So there's a component called and it just left me, a heat sequencer that we see in electric heating sometimes. You'll have a single stage of electric heat, but you'll have 3 circuits, and a heat sequencer is basically just a little heat activated switch. And what it is when you send it the call for heat, it will energize the first circuit of electric heat, and then it'll heat itself internally. And once it heats itself internally enough, it closes another set of contacts and possibly a third set of contacts. They were called heat sequencers. Other places you'll see heaters, old slow open gas valves, guys. The slow open gas valves are a heated gas valve. And as that heater heats up, it allows that gas valve to open slowly versus a solenoid actuated gas valve, which opens instantaneously. Hydronic zone valves can be heat actuated controls. Okay. So the generic symbol for a heater in your electrical wiring diagrams is that little zigzagged line. Okay. We've got all the things we're used to seeing out there. We've got our standard electric heat, got baseboards, radiant quartz, radiant in the floor, all that stuff. Okay. They're all just resistive heaters. Okay. More resistive heaters, crankcase, water heating elements. They're all just resistive heaters. This is just a giant resistor that generates heat. Okay. Talked about our gas valves, those old slow open gas valves. They had a little wax element in them, a very small one, and an electric heater there. Once that thing turned on, it heated that wax element fairly rapidly and allowed that valve to open. But it did it in a slow, controlled manner, so we didn't get a big backflash out of it. Okay. These guys, who's ever worked with a camstat? Okay, you just thought it was a high temperature limit in a really old furnace. Nope, it's got an electric heater in it. Okay. We couldn't rely on it. It wasn't 100% reliable to get enough radiant heat to trip, and so we had to bias it a little bit. So it's got a little radiant or a little electric heater up inside that camstat. These would be what I was referring to in heat sequencers. Time delays sometimes had basically they were a heat sequencer as well. But we had our source voltage up here, and it had a little heating element. Actually, I take that back. Source voltage was down here, had a little heating element. As that heat propagated through the heat sequencer, it would engage other sets of contacts. So they're everywhere, these little heaters. They're insidious. So heaters, how would we troubleshoot a heater, guys? What do you think? I've kind of given you some hints up to this point.
Test to see if you've got continuity through the coils.
You broke up there. Say that again.
Test to see if you've got continuity through your heater coils.
Yeah, that's pretty much what you can do, is just take your meter leads, put them across the heater, and you should have some resistance value. Now, heaters, they're usually a lot better about giving you resistance values from the manufacturers. But if you don't know what that resistance value is, you know that it should be something and not nothing and not open line. Okay, so those are the three results you can get. You can get a resistive reading, you can get an open line, or a shorted reading. Okay. Typically, comfort cooling or comfort heating resistive heaters are going to be in the kilo ohm range. Crankcase heaters are probably going to be in the kilo ohm range. Wax actuated zone valve for a radiant system may only be a couple hundred ohms. Okay. But you should have something there. If you have nothing or it's shorted, you know something's wrong. Okay. But it's just a big resistor. So we test it with resistance. Anytime you test with resistance, guys, what do you have to remember to do?
Disconnect.
Disconnect one side. Otherwise, you can get a ghost resistance through the connected circuit. Okay. Disconnect switches, guys. There's lots of disconnect switches out there. I'm really partial to the fused ones. I like my fingers. I like what sensation I have left in them. Now, the thing that people get hung up on is, I already have a breaker. Why would I need a fused disconnect? Why can't I just use that non-fused disconnect? What do you guys think? What's the job of a fuse in a disconnect switch? You guys think why would we put a fuse in a disconnect switch?
To prevent a fire.
Okay. Any others?
In case your breaker didn't work.
Okay. So fuses are there to protect the equipment. Is that a fair statement?
Yes.
Okay. What are breakers for?
to turn on and off the power.
Okay, that's one purpose of them, so they can be a disconnect switch. Okay, what else are breakers for?
Too much current. If you have too much current going through
Going through what?
the load.
Nope, they don't care about the load.
Okay.
Breakers are there to protect the wire. Okay, that's what breakers are designed to do. They're there to make sure not that the load connected to the wire doesn't draw enough current to make the wire ignite. Breakers are sized based off of what wire is in the wall. Okay, so that's why you see the electrical panels and all the 20 amp breakers have at least 12 gauge run to them, and all the 15 amp breakers only have 14 gauge wire hooked up to them. Because above 15 amps, that 14 gauge wire starts to heat up. So they go to, when they go above 15 amps, when they're wiring up a house, they're going to step up to that heavier gauge wire and go to a 20 amp breaker. Okay. Whereas your oven, 60, 70 amps, might have double aught wire to it, or number 8 or number 10. Okay. The breaker's job is to protect the wire and keep the house from burning down. It's not its job to protect the furnace or the air conditioner. Okay. Now, typically our furnaces are going to fall within the breaker size that's already there, so we don't get too concerned about that. Whereas our air conditioners may or may not. Okay. And a lot of times when we're going out and changing air conditioners, you may notice that you've got a 60 amp breaker on the air conditioner, but your air conditioner has something called a max fuse size. That's the maximum fuse that's going to protect your equipment. So disconnect switches, in my opinion, should always be fused in some way so that we can protect the equipment and we're not relying on the wire protection device to protect the equipment instead. Okay, so they come in all shapes and sizes, 1, 2, 3 pole, okay, with or without a neutral. They look like that. That's a beauty of one. All sorts of different varieties. Commercial ones that we talked about, that symbol with the handle. I actually have a giant knife switch on my unit at the garage because we replaced the disconnect switch for the forklift at my office, and suddenly free disconnect switch. Probably have the only 20 amp air conditioner with a 5-inch fuse protecting it. Okay, but in the end, guys, they are switches. Okay, so we can test a switch if it's closed. How much voltage should we read across it, guys?
None.
None.
Nothing. You shouldn't have any voltage across the closed switch. If it's open, what should we read?
Source
The
voltage.
difference.
Line voltage.
Yeah, whatever your source voltage is. Okay, here's the trick. Fuses are switches. That's all they are. The trick is they're a fuse that they're a switch that only works once. Okay, so we can test fuses the same way we test switches. A good fuse will have no voltage drop across it. A bad fuse will. Okay, let's actually pause here, guys. Let's take a 10-minute break. And let's be back here at 15 after 5, okay? And we'll keep going. So we'll do this generator demonstration from last week that I didn't have available. So if we look down inside this motor, and turn the light on for this, you can see we've got coils of wire. And as I spin this internal coil, you see that gray line where it gets darker right there. As I spin it, it gets darker again. This has a 3-magnet core. So this has 3 magnets that sit in it. And as I spin this, I can feel it indexing on all the iron cores around this motor as I spin it. Okay, and that's because the magnet's attracted to the iron core that's in the center of these coils. Now this one's a fairly low horsepower motor. You can kind of tell that by how much space we've got in between the coils. And it is a 3-pole or 3-phase motor. So we're only going to use 2 of them tonight. But basically all we've got is a bunch of magnets surrounded by an iron core. If this looks familiar, guys, it's because this is an X13 motor. And what we're going to do is we're going to spin it. I've got my fancy generator driver here. It's just my 18-volt drill chucked up to the end of this thing. We're gonna pull this up here a little bit. And we're gonna drag the meter up here. We'll set it for voltage. Jam some probes in here. Okay. And as I spin this motor, you'll notice that we're starting to generate electricity. As I spin it faster, we generate more electricity. If I get that thing cooking, I get all the way up to 200 volts. Okay. Here's something unique about the power coming out of this motor. Okay. We talked about frequency being the number of times that the motor goes from 0 volts up to 60, back down to -60 and back. So we're generating 120 volts that comes out of the wall, but we're doing it 60 times per second. Okay. That frequency is directly proportional to how many times the magnetic field passes across your winding, your electrical windings, so your coils of wire. So I've actually got 3 magnets in this thing. Okay. If I had 1 magnet and I ran this thing across 1 coil of wire at 60 RPM, I'd get 60 Hertz. Okay. So I've switched my meter over to frequency, and what you'll notice is that I'm at about half speed and I'm running 60 Hertz. Okay. If I go to full speed, thing tops out around 180 Hertz. Okay. And at 180 Hertz, I'm doing 220 volts. Okay. Now we can do some fun things with this. So I'm going to back this off here a little bit. My desk space is not large enough, said every person ever. Okay. And we're going to pull my power source out here. Now I have my power source disconnected from the wall at the moment. But what I'm going to do is I'm going to take those same leads we were using to power this other motor over here last week, and I'm going to hook it up into my power source onto my motor. So I've got right here, got my black to black, and we're going to use my blue phase for neutral. Okay. And let's do something useful with this power. So we've got a little electric light here. Turn my light off. And what we'll notice is as I spin this up, we're going to cross the threshold at which the LEDs are going to power up. Okay. The faster I spin it, the brighter that guy gets. Okay, so we generate more and less voltage to run through that set of light bulbs. Okay, the instant I stop, it cuts the voltage off. Okay, so that's fine and dandy. But here's something interesting. Okay, so LEDs are pretty tolerant of a high frequency power source. Okay. I told you guys every time I do this class, it costs me a motor. So I'm going to disconnect it here, and let's see if we can actually get this thing to do anything. Okay, so we've got our PSC motor here, and we're just going to wire these two motors together. Okay, so we've got our high speed here. I can get up to connect. Come on, there we go. Okay, and we'll hook them up to two of these phases here. Okay, and what do you guys think is going to happen if I run this, turn on this generator here?
It'll run, but the hertz is going to be something different, maybe.
Yeah, so this is designed to be run off of 60 hertz and 115 volts. We're going to feed it. What was my frequency at the top end, guys? Anybody remember?
Wasn't it like
I don't
220
remember.
or something?
Yeah, and then the voltage was way high too. Okay, so we're going to run high frequency, high voltage, and let's see what happens. So I'm going to put my amp meter here just to see how many amps we're going to draw. Okay, and here we go. We get anything? I was too busy closing my eyes.
1.4.
It's like 1.4.
We got some amperage. Did my motor move?
Couldn't tell.
No,
Tell-
it didn't. There, well, we'll put the shaft up so it's a little easier to see that indexing. We'll come down to it. Okay, so maybe I was spinning it the wrong way. I'll spin the generator the other way here. Nope, no amperage. Okay, now remember what this motor was supposed to run at? Anybody recall? So high speed should have been around 5-6 amps. We're only putting 1.4 amps into it. So we don't have enough power to start this thing in high speed. Okay. What if we went to low speed? Do you think it'd start?
No.
Who remembers what color was low?
Red.
Red? Okay, we'll try red. All right, let's try red. Look at that. Okay, we got it to spin. So it's important that even though we're able to generate power here, if we want to do useful work for it, we've got to match our frequency and our voltage. Okay, so we're running really high voltage, really high frequency, and you notice this thing soft starts. Okay, and that's because we're running that frequency so high through those windings that it has a tough time grabbing hold of that rotor and getting it moving. It's just not designed to run at that high frequency. But we can get power out simply by spinning magnets around a coil of wire. Okay, and that's how commercial power generation is achieved. Then they run it through a whole bunch of circuitry to make it usable for us. Cool.
Yep, it's cool.
Yes, that is cool. It was only like 1.2 amps still, but it still went.
Yeah. So we
How bad is that on the start windings?
yeah, that motor's not going to live very long powering it that way. I can guarantee you that, because yeah, it'll heat up and toast that thing pretty quick. but it is possible to generate your own power. You've just got to condition it once it comes out of your generator. So when you buy an electric generator at the hardware store, you're not paying for the engine, you're paying for the big electronics package that comes with it to make that power usable. Okay. Any questions, guys? Okay. So we're gonna go back into switches here. So we got all kinds of switches in our industry that help us do what we do for a living. So one of those is a flow switch. We're just going to go through a lot of symbols here, guys. We're not going to talk about troubleshooting on every single one of these too specifically, because in the end, they're switches. So flow switches kind of look like that. They've got a flag on them. You see these a lot in fluid or airflow situations where they're trying to prove airflow or fluid flow. And it's a switch, guys. If you have flow, you can verify that you have flow. You should have a closed or open switch, depending on what type it is. Okay. Pressure switches. Anybody seen a pressure switch in our industry? Where might you encounter a pressure switch?
In the furnace.
Furnace has pressure switches for the venter motors. Anywhere else?
Condenser units.
Yep. Pressure safeties for the refrigeration system. Okay. We got a couple different ones pictured here. We have a single port pressure switch, which just senses pressure from one zone. This would be a normally closed one. We have dual pressure switches, which the symbol will have two diaphragms pictured on it, where we sense pressure from two different pressure zones and take the difference between them. And then we've also got manual reset pressure switches, which look like this. They'll have, usually they're single zone pressure switches, and then they've got a little stick that comes up on them on the wiring diagram. That indicates that it is a manual reset button on that. Okay. We use them for air pressure, liquid pressure, all sorts of stuff, refrigerant pressure, okay, all sorts of stuff. But in the end, they're switches, guys. They're open or closed. You can take voltage or resistance through them in any position. Okay. Let's talk a little bit about overloads. So now we're into safety devices. So we've got several different types of overloads. We've got thermal overloads. We've got current overloads, current magnetic overloads. Okay. Various different types. Let's talk about some symbols. So a thermal overload is typically going to be depicted by having two contacts and usually a bent line in between them. This is indicating that this is a bimetal disc. When that thing heats up, it will curl up and actually break it. They're actually just pictorially describing what's going on inside that switch. When the current gets high enough, this little metal reed will actually coil up and separate itself from that other contact. Current sensing overloads are simply two of those little bimetal discs a lot of times, and they will curl and separate from each other under heat, which would be an indication of high current. Current magnetic ones are using their circuit to break a set of relays. So this is just a solenoid activated current sensing relay. Okay, but in the end, guys, these are all just glorified switches, thermally activated switches, whether they're direct acted thermal like this one, or if they're electrical heat generation thermal overloads like this one. They're all just switches. They're open or closed. They have two positions. You can sense voltage through them or you can't. Okay. Limit switches comes in lots of varieties. Auto reset, manual reset, rollout switches, temperature range switches. Okay, lots of them out there. We got various symbols for them. Which one of those is the manual reset, guys?
Little stick at the top left.
Top left one, because you got that little stick. That's kind of the dead giveaway on any kind of safety or overload or switch, that it's a manual reset. It's going to have that button depicted there. So these are both open on rise pressure switches, or excuse me, temperature switches. This one would be a close on a drop in temperature switch here. Okay. But again, guys, these are switches. Push button switches. You can have all types of push button switches, normally open ones, would look like that. Different symbols for them. This would be a normally closed one right here, normally open. This one's actually a latching switch. Or excuse me, this one's a latching switch. This one's a momentary switch. But again, they're switches, guys. Let's talk about thermostats. So what's a thermostat, guys? What is it really?
It's a switch.
It's a box full of thermally sensitive switches. Okay, heating, cooling, doesn't matter. It's a thermally activated switch, guys. Okay, now in the age of digital, instead of thermally activated switches, we get relay activated switches. Okay, so like Keith says, switches are always going to be shown in their de-energized state on the wiring diagrams, unless otherwise noted. Okay, but modern thermostats, rather than having thermally activated switches in them, the digital thermostats, we're just using a temperature sensor to operate a relay, which again is just a switch. Okay, our industry lives and dies by switches. So two different types of switches here. We have an open on rise, and here we have a close on rise. So you can see the difference in how those are depicted. So this one, as the temperature rises, it's going to close the switch. This one, as the temperature rises, it's going to open the switch. Okay, but again, they're switches. Time delays. These can get a little trickier because you can have a delay on make. So this is a time delay that delays a set amount of time when it's energized. So this would be a delay on switch or a delay on make. You can have delay on breaks. This would be a delay when you de-energize it. It's going to stay closed for a certain amount of time. Or you can also have interval switches. So we have things that like defrost timers would be an interval type switch. Repeat switches would be like interlocks. And again, defrost timers would be something like that always hits at a certain time. I've never seen a one-shot time delay switch used in a air conditioning heating system. That's more of a microelectronics thing. Okay, but in the end, guys, these are all switches. So time delays are typically pictured as a arrow. So this would be a delay on make down below, and this would be a delay on break. Okay. The trick with time delay switches is you not only have the switch to diagnose, you also have the time component to diagnose. So this is where a stopwatch comes in real handy, because I don't know about you, but standing in front of something, waiting for something to activate, time stretches off into eternity. 30 seconds becomes 5 minutes, and I can't trust myself. So used to do this a lot with ice machines. I had a stopwatch that I hung on the unit so that I could sit there and time defrost cycles or time harvest cycles or anything like that, because those were time critical devices. There was a lot of time delays in them. And the only way to test a time delay switch is to activate it and see if the timing's correct. Okay. But again, they're switches. Breakers, guys, we already kind of talked about. They come in lots of flavors. 1, 2, or 3 pole breakers typically is what we're going to see. HVACR rated breakers. There is a big trend in our industry and local municipalities to require on condensing furnaces GFI breakers, which is, I suppose, makes sense to somebody because we have a water generating appliance. They want to have a GFI on it. The only place that falls down is when we have a variable speed motor in it of any variety, whether that's an inducer motor or a blower motor, or the new constant torque motors as well do not get along with GFI breakers because they are frequency driven motors. They reference the ground for their operations and they will trip GFIs. So when we talk about HVACR breaker, it's rated for HVAC equipment. Okay. So lots of different breakers down here, lots of symbols for them, but generally what they are is they are a thermal activated switch. So you're going to see that bimetal thermal type thing there. A 3-pole breaker is going to have 3 of them all tied together. Okay. But a breaker is really something that it's a current sensing breaker, essentially. Okay. So as too much current passes through that breaker, it's going to heat those bimetal switch analogs, and it's going to open up the breaker all at once because they're all tied together. Okay. But in the end, they're a switch, guys. We talked a little bit about fuses already. So fuses are simply they have an element in them that melts at a set value of current. There's lots of different symbols for them. These are the 2 most common ones that you'll see, either a box with 2 lines in it or the fusible link type symbol right there. Okay. Fusible links are single use fuses, typically used as rollout switches in older furnaces. Last chance high limits, things like that are listed as fusible links. Other types of switches you'll have, guys, are humidistats. So this would be a humidity sensing switch. Opens on a rise in humidity, closes on a drop in humidity. So this would be for a humidifier, not a dehumidifier. Float controls, we see these in high-end swamp coolers. We see them in hydronic systems, steam boilers, things like that. And this is basically just a float attached to a switch. Okay. Fan controls, these are just thermal switches. Anybody who's ever had a low boy or a furnace older than about 25 years, you'll see these auxiliary fan controls outside the furnace or inside the furnace sometimes. They're becoming rarer. But in the end, guys, they're all just switches. Okay. Any questions, guys, about any of the stuff we've covered? Okay. So let's get off of switches here, because I don't know about you, but I've had about as much switch talk as I can stand. And let's talk about some other devices. So diodes. So diodes are kind of fun little devices. We've got a couple symbols for diodes here. Sometimes you'll just see the line with the arrow, and sometimes you'll have a diode with a drain, I believe is what's pictured here. So we have the circle and a couple arrows. Diodes are really the check valves of the electrical system. So diodes allow electricity to flow in one direction. So the offshoot of this is if you put AC current in here, it's only going to allow either the positive or the negative side of the current to go through the diode. Okay. And so we got lots of different applications. We've got one that's pictured down here. This is a set of diodes in the bridge. We'll talk about what that does a little later. But diodes are simply electrical check valves. Okay, troubleshooting, and my slide didn't populate properly. So troubleshooting diodes is fairly easy. So I've got my meter here. Flip up the camera, and I've got a couple different diodes here. So while I'm setting that up, that's not what I wanted. Where'd it go? Never a good day when you misplace your diodes, guys. All right, we'll use a different one. That's disconcerting. That one was rather expensive. Let's pop off of here. So this diode bridge you see down here is actually what's called a rectifier bridge. And this is for taking AC current and changing it into DC current. So we've actually got two different sets of diodes. We've got our AC current coming in the bottom, it does not allow voltage to flow in this direction, but it does allow voltage to flow in that direction. Same thing on the top. We don't allow voltage to flow in this direction or this direction, but we do allow it to flow in this direction. What this essentially does is it divides the voltage into a DC signal that comes out of this. Okay. So we allow DC voltage to flow out of this side of the bridge rectifier through our load and then back to equalize with the AC current through these two sides. Okay. Now diodes allow voltage to move in one direction and not the other. And I just found my slide that I needed. So it still didn't work. And stop pulling out my pictures. So we'll do it this way. Okay, so there's my bridge rectifier. But diodes are pretty easy to diagnose with a meter. You put AC voltage into the diode, you should get a dropped DC voltage on the other side. The other thing that a lot of guys don't realize that their meter has is a diode checker. And most guys don't know that it's there because they don't know what to look for. So I'm going to show you on this meter. Okay. But here's my electrical meter I've got here, guys. And you'll notice down by my capacitor setting, I've got in the yellow here something that looks an awful lot like the symbol for a diode right there. Okay, so I'm going to take my meter here and I'm going to put it on my capacitor, and then I'm going to hit my option button here and switch it to a diode check. So diodes are kind of funny in that I've got a diode built into this. It happens to be a light emitting diode. And so what my meter is going to do is it's going to put a small amount of voltage out on my red lead here. And it's going to look for that voltage to return on my black lead here. So I've got, if I can find the right wires here, this is a little switch with a LED in it. If I find the right probes and get them on the right way, we'll notice that it is passing a small amount of current through that light emitting diode. It actually lights the diode in this case when I do my diode test. Okay. So when we talk about light emitting diodes, it's really just that electrical check valve. And when we push a little DC voltage through it in the right direction, it lights up that diode. Okay. So that's one way you can check a diode. The other way you can check a diode is put your meter onto resistance, and you should be able to get resistance through it one direction. Because again, my meter is putting voltage out. So I'm on two of the sides here, and I don't get any voltage or ohm reading there. But if I reverse my polarity, I should get, if I get on it correctly, hang on here, guys. Come on, work with me here. This is why I wanted my expensive diode. This one doesn't want to cooperate. This one has some extra electronics in it, just to be difficult. There we go. So there's my diode. I'm hooked up on either side of my diode. You'll see that I've got some mega ohm resistance there through that diode. It's a pretty high resistance diode. And what it's doing is if I go through one direction of the diode, I'll get resistance through it. If I go the other direction, it's just open line. So there's the other direction here. And I'm just reading OL. So that's another way you can test a diode. If you get resistance through both directions on the diode, you know your diode's bad. It's no longer acting as a check valve. I really wish I had that other diode. It was much easier to see. Apologize for that, guys. So, couple little tricks for your meter. You can check diodes. Now, where would we find such a device? So, let me pop back into my presentation here. So this little device right here is actually a bridge rectifier that comes out of an air conditioner. So you'll find this in a 2-step scroll compressor air conditioner. And what this does is they have found that the little solenoid that's inside the compressor has a longer lifespan if you run it off a DC voltage versus AC voltage. And so they actually take this little bridge rectifier, they convert 24 volts AC into 21 volts DC with this little device. And they run that solenoid off of DC voltage rather than AC voltage just to make it last longer. Cool. Any questions about diodes, guys?
Would you be able to go through how they turn the sine wave into a DC sine wave at all? Like
Sure.
that?
Sure. Let me grab a sheet of paper. Let's look at that. We'll flip back to my overhead here. Grab a couple clean sheets of paper here. So Mitsubishi does this a lot. So if some of you who have been through a Mitsubishi class will find this familiar. So grab a pen. Here a little closer. So basically we've got my bridge rectifier here. Okay. And we're going to feed AC voltage into it up here. Okay. And this AC voltage looks like this. So we've got my AC voltage here. Okay. And then we feed it through the rectifier. Okay. So this little thing that I'm going to show you here is coming in this side, comes in, hits this little diode right here. And what this diode does is only allows voltage from one side of the sine wave. So we go through that rectifier, and what we end up with is this half of the sine wave. Okay. And it does not allow the voltage to move in that direction, or the negative side. And so it chops all this side of the sine wave out. Okay. So we've gotten rid of all that. So that's doing that here. On this part of this diode, what it's doing is it's taking that AC voltage. I'm going to move up here. Got my AC voltage sine wave here. And we go through the diode. We'll picture this one a little better. So I got my diode here. And what this is going to allow is it's going to cut out all the top side and just include the bottom. Okay. And so we split it. What Mitsubishi does in this is they take multiple phases. So they're running 2-phase power. So 100 or 240 volts. And they end up with 2 phases that they've chopped it out of on either side. Okay. With their 2 phases of power. So they end up with a positive DC signal and a negative DC signal. Okay. And what we can do is we can take those DC signals and you can make it smoother or easier. Mitsubishi does that. They run it through a big smoothing circuit with a bunch of capacitors to kind of, instead of having a pulse DC, kind of smooths that out a little bit. Okay, you can do lots of stuff with that DC signal. But what we're doing in here is we're just chopping off one side of it because we've only got 24 volts AC right here. And it's a single phase. So what's coming out of this, instead of the sine wave that we're putting into it, we're getting a DC out of it. Okay, so we end up with little pulses of DC that come out. They're fed through the solenoid coil, and then they keep coming back all the way back to the return. Okay, and they're allowed to recombine with the AC voltage over here because the check valves on these diodes go this way and that way. Okay.
Now,
That's kind of
diodes-
simplified version of what we're doing here.
are the diodes blocking like electrons from the negative side of the?
That's exactly what they're doing. They're blocking the flow of electrons in one direction.
All right. Thank you.
So when we run a single phase circuit through this, it gives us a pulse DC. When we run a 230 volt or two phase system through this, we get a higher frequency of pulses. Okay. And then what Mitsubishi does is they take this higher frequency of pulses, they run it through what they call a smoothing circuit, so that instead of it being really dramatic like that, it comes out of the smoothing circuit kind of more like this. Okay. And then they use that to drive their variable speed stuff.
And you said that was capacitors that smooth it out?
Yeah, they use a series of capacitors to smooth that out.
Okay.
But in the end, it's all comes back to this little device here called a bridge rectifier. And it's just 4 diodes arranged in such a way that they only allow voltage to come out one way. Now, you know, combine those, do multiples of them to do all sorts of fun, fancy things, but it's just DC voltage rectification. So when you hear of AC being rectified to DC, this is what they're doing. They're just cutting part of that sine wave out and just using what they want of it, which is that one positive or negative side. Mitsubishi actually uses both, kind of like we showed down here. You know, they'll put the positive side to work on one side, negative side to work on the one side. And then they eventually recombine it to make, they take single phase power and turn it into three phase power doing this, but that's a whole nother class. Any questions, guys?
Are they able to use more electric motive force that way?
Converting it to DC, it can make it easier to amplify or transform that voltage to a higher voltage, and moving it into 3-phase can give them some torque advantages on motors and control over that voltage a lot. So that's one of the purposes of switching to DC, is to just give an added level of control and manipulation to that power.
But with you're saying Mitsubishi uses the positive and the negative side on separate things, does that
Yeah,
allow
they do.
more use of the energy?
Yeah, they use them for different things inside their control packages, and then they actually recombine them and make AC power again on the outlet of those.
Okay.
But the reason we see that rectifier in the ACs is simply to extend the life of that solenoid, because you can't change it. That solenoid's non-serviceable in those compressors. So try to make that solenoid last as long as the unit. Any other questions, guys? We talked about diodes. So the reason we talk about diodes is what we're doing when we check flame current. So flame current is actually an electrical property. We're using a rectification circuit, just like we used with diodes. We're changing AC voltage to DC voltage, but we're using the actual flame of a burner. Flames have this interesting little property that they will actually rectify AC to DC current. Okay. And so if we equate this to a flame sensor, what we're trying to do is we've got our flame sensor over here. That's our post. And we got a guy with a shotgun. So we're gonna assume that this guy has a shotgun that shoots perfect circles of pellets, and he's only got pellets on the outer perimeter of this circle. So this is our shotgun that shoots rings of pellets. Okay, and what that simulates and what that equates to is the flame coming out of a burner. Okay. Flames are actually electrically conductive to a small degree, but they're only electrically conductive where the flame is actually burning. Okay, so the flame acts out of a burner actually only has an active flame on the exterior part of the flame. And so what we're doing when we do flame current is we actually send a high voltage signal, sometimes up to 120 volts in residential stuff, up through that flame sensor, or this is our post. So if we have this guy with a shotgun and we have him shoot at that post, where is that post going to receive pellets?
The lower third.
Yeah, it's just going to get pellets down here where that outer ring. Okay, so what we do with flame sensors is, you'll notice flame sensors are typically positioned kind of over in this section. So the flame sensor, if we move that over here, is actually going to pick up 2 points on that circle. Okay, and what we do is we pass AC voltage up this flame sensor, and it rectifies to DC through the flame and goes to ground at the face of the burner. So this is what's called DC flame rectification. And we end up being able to measure how much current we're drawing through that circuit. And so when we talk about flame current, we're actually talking about the DC current that's being rectified through our flame sensor. So this brings up a good point. When you guys are testing flame current, it might be a good idea not to hold on to it with your fingers, because we are sending up to 120 volts through these flame sensors. I've worked on commercial equipment that sends 230 volts out to a flame sensor before, and it'll light up your life a little bit. But basically that's what the control board is doing, is we're taking that flame sensor and we're manipulating it so that we have as much current passing through the flame sensor to ground as we can. So that's why you see flame sensors not posted right in the middle like this one is, but off to the side so that they can pick up more of the perimeter of that flame current. Ideally, you'd have your flame sensor cut right through the edge of the flame to pick up as much of that actively burning flame as you can to get as high a flame current as you could. Okay, so this is measured in microamps. Yes, sir.
You can't be shocked if you touch the flames, right? It's just super low current.
Well, you'll burn yourself before you shock yourself. While they are conductive, they're very poor conductors because we're actually measuring millionths of an amp through those flames. Now, if you hold on to the flame sensor, it might light up your life a little bit.
Yeah, it's cool that the flames do carry this a little bit of the charge, though.
Yeah, but that, I mean, we're talking millionths of an amp. Okay, so it's not enough to damage you, but it will hurt if you hold on to that flame sensor and ground out. Okay, so the higher the voltage, the higher the flame signal you're going to get. So you'll see some equipment run 24 volts up to that flame sensor, and some of it runs as high as 120 volts. The modulating furnaces guys almost universally run 120 volts through that flame sensor because they've got very little flame to deal with. And so they need to boost that flame sensor as high as they can get it. Okay, so a typical microamp may be as low as 0.02. This is generally not very, very, very bad. And generally, we're not going to see higher than 7 microamps. So you'll see this on some commercial equipment. Radiant burners tend to get a little higher microamp reading. Typical furnace is going to be around 3 to 3.5, and most of them lock out below 1 microamp. Okay, we measure that with a microamp meter, which again, on your meter is that little U shape with an A, okay, on your meter. Okay. So flame sensors are kind of interesting electrical devices in and of themselves. They're not terribly complicated. They're stainless steel rods with porcelain isolators. Okay. So when we talk about stainless steel rods and flame sensors, things that will cause flame sensors not to work electrically are anything that's going to insulate that signal. Okay. So what might be something that you could get on a flame sensor in a normal environment that would cause your flame sensor to be insulated electrically?
Soot.
Come again?
Soot.
Soot? Yeah, absolutely. Soot's not very electrically conductive. Anything else that gets on our flame sensors?
Our furnaces are installed in a laundry room. I've seen that laundry fabric softeners, that type of thing gets in the air.
Yep, chemicals will corrode flame sensors and it makes them rust. You can rust a stainless steel rod. It's not that it doesn't rust, it just doesn't rust as readily. So chemical environments will cause buildup or rust on flame sensors, and that stuff's all not electrically conductive. Okay. So in order to get a flame sensor to work again, all we have to do is clean it. Okay. And because it's a polished rod, we want to just take the crap off of it without taking the polish off of that rod. If we use a file or something like that to clean that flame sensor, all we're doing is adding surface area. We're putting big grooves in that flame sensor, adds surface area to that flame sensor, which on the surface may seem like a good thing, but what it really does is it makes it more prone to fouling. Okay. So when we talk about cleaning stainless steel rods, the favorite one I always hear is guys say, oh, just use a dollar bill. That's a heck of an expensive way to clean a flame sensor, in my opinion, because I don't know about you, but when I was a tech, if you touched something with a flame sensor, you cleaned it, period. The end. 7, 8 service calls a day, that can get pretty pricey. So what we want to do is use something that's just going to take the crap off of the flame sensor, but not touch the polish on the flame sensor. So things like double or triple aught steel wool work. Steel wool makes kind of a mess in your bag when it gets wet, so I generally don't recommend that. What I found worked really well for me was just the green Scotch-Brite pads. They're very mildly abrasive. It's just abrasive enough to just take that crap off of the flame sensor, but not to put grooves and just repolish that flame sensor really nicely. Other things, like I said, double aught steel wool, things that are just not very abrasive at all. So things that I don't recommend are the concrete floor in the mechanical room, the file in your Leatherman, things like that are just going to destroy your flame sensor and make you have to clean it more often. Any questions, guys? So the worst flame sensors I ever saw was in a boiler that was in a dry cleaner. And anybody who's ever been into a dry cleaner knows that they use all kinds of chemicals in there. Most of them, by the way, are corrosive. But we would actually go out and replace the flame sensor every year in this boiler, just because it would eat away at this flame sensor so badly that it was unusable every heating season. Okay.
How'd the heat exchange look?
The heat exchanger, we would get about 3 years out of a furnace in that place. That's why we moved them to a boiler. So
Okay.
the boiler was okay because it used a stainless steel boiler exchanger, but we would have to pour muriatic acid into the boiler every year. Our bigger problem there was buildup of debris inside the boiler from all the things that got burned off. Any other questions, guys? Okay, let's talk about thermocouples because they're a little different. Thermocouples are kind of fun little devices, and in their root, all they really are is two pieces of metal. So we've got we've got what we call an outer element and an inner element. And all they are is two different types of metal. Usually we have a stainless steel on the outside and some type of copper alloy inside. And they're welded together at the outlet or at the tip of this flame sensor. And the fun thing about differentiated metals is anytime you heat two pieces of metal that are joined together, they will generate a small amount of electricity. So that's what a thermocouple is. It's just a little micro generator. It's a thermally activated generator. Okay, and so we put these little thermocouples into the flame right at the tip, is where we want that flame to be. And we heat that little thermocouple up until it generates enough electricity to hold the pilot solenoid on a gas valve open. Okay, so that little pilot solenoid is a very, very small solenoid that allows just enough gas through to keep the pilot light lit. Okay, on these things. It also generates, if you need something that generates a little more power, we can go to a little different device that we'll talk about in a second. The thing to remember is thermocouples are just little DC voltage generators measured in the millivolts, typically around 37 millivolts, I believe, if my memory serves properly. There's the electrical symbol for a thermocouple. If we need a little more voltage for something like a fireplace, we can do a thermopile, which is very aptly named because it's just a bunch of thermocouples jammed into a single housing. So it's a pile of thermocouples. And these things will range anywhere from 370 millivolts up to 700 millivolts, depending on what you're using them for. But we'll use these guys to generate a little more power for larger gas valves or things like fireplaces, things like that. And it's just a bunch of thermocouples all in series. Okay. Same troubleshooting as a thermocouple, though. Basically, you get it hot, it should generate electricity. If you don't, it's usually the hot junction that has failed inside that thermocouple, and it's time to replace the thermocouple. Other devices that you'll see on wiring diagrams is the dreaded black box. Looks like that. Usually has some wires poking out of it. This is generally used to designate solid state electronics that you can't do anything with. That's a battery. Hot surface igniters. These are just heaters, guys, so they ohm out or they don't. Every hot surface igniter has a different ohm rating, so refer to your OEM for that. Other things you'll see on wiring diagrams is a line with a bunch of slashes through it. So this is shorthand for doing a multi-wire conductor. This one has 4 conductors inside the one cable. Little circles with R's are usually terminals. That would be a terminal R, it could be anything listed in there. These are Molex connectors. You'll see the little arrows, male and female versions of them. These are little plastic plugs. Okay. But that being said, let's dive into wiring diagrams here, guys. So this is a type of wiring diagram called a pictorial wiring diagram. It shows your components and then shows what they are electrically inside them. This is kind of a wiring diagram that's fallen out of favor in the last 20 years. But you used to see this a lot on older equipment. They'd have a picture of the device and then a description of it, how it worked electrically. They were really nice for some things, in that you could see generally what your equipment looked like, you know, what the device should be shaped like, what you're looking for. But they were kind of a pain in the butt for diagnostics because they weren't very linear. So these are just basic wiring diagrams. Anytime you have a wiring diagram, you're going to have a source, a path, and some kind of load. This would be a short, no load. This would be an open where you've got a break between the load. Okay. various different ways of just depicting wiring diagrams, but they're all going to have source voltage, a path, and a load on your wiring diagrams. So series circuits we already talked about when we talked about resistors. Parallel circuits we talked about when we talked about resistors. And then you can combine the two to make series parallel circuits. And you'll see mostly this stuff in wiring diagrams these days, in ladder diagrams. Okay. So any wiring diagram is going to have a power supply. It's going to have some type of path that it shows. You're going to have your loads. You're going to have your controls or your switches. And usually there's something that tells you what everything means. So it'll have symbols. If your wiring diagram is really good, you might have a locator system built into it. So we've got lots of different wiring diagrams out there. So some of them are simplified for installation or field wiring. We've got line or pictorial wiring diagrams. We looked at that pictorial a minute ago. Ladder or schematics. And they're all useful for different things. So installation or a field wiring diagram just takes that wiring down to the bare bones of what the installer needs to do. Okay. So the installer on this one needs to run thermostat connections and line voltage connections. They'll usually have a couple different options for the low voltage configurations, depending on what you're doing, what you're connecting to. We've got our, we've got our little legend down here that tells us what each of the different wiring designators are. Okay. Tells us what we're doing. And this is just a bare bones. This is what you need to make the thing run wiring diagram. Okay. Not terribly useful for diagnostics typically. But it's just going to give you your factory field wiring diagram. Is going to have your wiring points, your connection points, labels, and things like that. Wire requirements are also listed there typically. Sometimes it'll have colors. Okay. You guys ever looked at the wire, the writing on wires, guys? Anybody ever paid attention to it?
No.
I've seen it,
Yeah.
but not real familiar with the lingo on there.
Yeah, there's a lot of information that you can pull off a wire. This becomes important if you're going to go to replace something. You'll notice that this one has the insulation type here as a TEW. It has a thermal rating on that insulation, which is 105 C. Okay, you can usually Google this stuff and come up with answers. Or if you've invested in one of those little uglies reference books that I talked about last week, it has a whole section in here about interpreting wiring nomenclature. So comes in handy for that if you're going to have to replace something. So make sure you're paying attention to your wire. You know, you've got white with stripe, black with stripe, blue, orange, yellow, white with yellow stripe, you know. So this is all stuff we got to go to your legend for to find that. So line or pictorial wiring diagrams are what you see here. Kind of talked about that pictorial diagram. It's nice to identify components. Line diagrams have kind of taken the place. It gives you a general idea of your component layout in the circuit. So this can be fairly handy for tracing circuits. It's very, very linear. I lived and died with a set of highlighters in my hand on these wiring diagrams because I just couldn't keep track of the wires. And so I just physically traced the wiring diagram. But it allows you to go from device to device to device very easily just by tracing your physical wires. See all the switches it goes through out to where it controls whatever you're trying to control. So they can be useful for that. Usually shows them physical locations, all the connection designators, wire designators, all that stuff is useful. This is really good for tracing components. Ladder diagrams are what I find to be a lot better for diagnosing stuff because it has each circuit broken out in a linear fashion. Now, this doesn't tell you where anything is, so you usually use this in conjunction with something else, but this has a lot of really excellent information built into it. All right, so let's pull some stuff up here on this guy. So here's a blown up version of one of those ladder diagrams. So we have power down the left and right. So let's focus on this bottom part of this for now. So we've got our transformer here. It converts this to from 208 or 230 volts into 115 volts. And we've got our neutral down one side and we've got our power down the other side. So we've got this fuse, okay, gives us our fuse designator and our amperage rating. And let's just say we were trying to figure out why my compressor is not coming on, my first stage compressor. Okay. And so we can come down here and we've got this first branch here, which says CR1A. Okay. So this tells me this is my control relay 1A, and it's got a normally open set of contacts. Okay. So assuming that that's closed, we can check that with a meter. We can then move down and we can come down here. So this is my OFMC. So this is my outdoor fan motor. So if we've closed this relay right here, we should be able to come and close this relay. So this circle here designates that this is a relay. And if we come out to the side of this, we know this is going to close some switches, but we don't necessarily know where all those switches are. This is what we're talking about when we talk about locators. So this comes in with large wiring diagrams. You'll notice this locator is a little tough to read, but it says 22,24. Come over to the right-hand side of this wiring diagram, you'll notice that every line in the wiring diagram is numbered. Okay, so we know that on this line, we've got a component that services something on line 22 and line 24. So if we come up here to line 22, we'll notice that line 22 lines up with this OFMC1 designator, and it's got a set of normally open contacts. Well, this is OFMC1 relay, so this is my OMFC1 normally open contacts. If we look at line 24, they line up with the other set of contacts from OFMC1. Okay, so this becomes really handy for diagnosing stuff because we can literally go through something, okay, in a very linear fashion and find out where it goes. The only part it gets tricky at is locating where the other stuff is, but that's what the locator designators are for here. Okay. Other things that you'll find on this diagram and diagrams like it is you'll have the wiring designators here. They'll either be call out colors or numbers, or they'll call out both. So this becomes really useful when you're doing point-to-point testing, because you may have one side of this wire that originates on one end of the unit and the other side of the wire terminates at the other end of the unit. And you can test it here, but who knows if that wire is broken or somewhere between that compressor and this point here. And inside a rooftop unit, you may have a dozen or 2 dozen wires all zip tied into a big bundle. It's a giant pain in the butt. Okay. But if you can locate the item and get the wire number on it, so this one might be designated yellow 246, that stuff is printed on the wires at the ends. And so you can go up to the contactor, find yellow 126, and then go down because you know it terminates on the common terminal of the compressor, and make sure that this wire is wire 126 down here. Make sure that somebody didn't come in and rewire the thing and find that your wire 126 is on your start winding or your run winding. Okay. So it makes it easy to identify stuff inside of units with these designators that it'll call out. This one's a pretty simple one, so it's just got a color code. But if you have a wire number here, that wire will be labeled with that wire number at both ends of that wire. And so it makes identifying things fairly easy. Okay. So here's just a basic furnace wiring diagram. I'm not gonna play with this one. Let's go to a piece of current equipment. So I'm gonna come out here to comfort site and we'll pull up a wiring diagram for an S9 furnace here. Nope, that's my email. Let's pull up Chrome here. I'm going to log into comfort site and let's pull a wiring diagram. Let's go product info. S9 furnace here. And we'll just pull the same wiring diagram that's inside the furnace. So there's my wiring diagram that's inside the furnace. You'll notice this is a pictorial wiring diagram. We've got several different versions of it. So there's the simplified one. And this is the one with everything on it. Okay, so if we blow this up here, you'll notice we've got all our notes up at the top. Back off one here. But we've got all of our wires here, and you'll notice that they're marked PR54. So this is wire purple 54. And you'll notice it also tells you it goes between the inducer limit and the condensate limit. So you can go to the end of that wire at the inducer limit, and it will be labeled 54, and it's purple. And you can go to the condensate switch and make sure that that wire lands at the right point on the condensate switch. Make sure that you haven't gotten PR4 over here and PR54 over here, because that's going to create problems. Okay, so it makes it really easy to trace wires through equipment with some of these designators once you know what they are. Okay. So if we're going to go out and do a diagnosis on this, and this does require you to understand a little bit about sequence of operation, but we can first check to make sure that our furnace is getting a call for heat. So we can check for voltage between W1 and my common wire, which is this BC terminal here. Okay, that tells me that the switch in the thermostat has closed if we've got 24 volts between W1 and common. So if we see 24 volts there, we know that the thermostat's calling for heat. At that point, we can start tracking down our sequence of operation. So the first thing that happens in a furnace is it's going to go out and check all its safeties. So we should be able to come out here to all of our safety devices. Okay, my limits, my condensate switches, all my flame rollouts. Okay, they're all going to be energized. Okay, and it's really handy that they've given us a junction up here. So we've got a little plug, and we can actually check for voltage across this plug, because it's going to go out and go through all of these for us. So it allows us to shortcut that. Now, if these are all closed here, guys, so we've got 2 flame rollouts and a thermal limit, what should my voltage be between these 2 terminals?
0.
Should be 0, because I'm just checking for closed switches, which are 0 voltage drop. Now, if we were to measure from one of these terminals to ground, what would we see?
24, something like that.
Yeah, we should see our control voltage there. So 24 volts in this case. Okay, so we can go out and we can check all of our switches, make sure they're all in the proper position. Okay, moving through the sequence of operation, we know that it's going to start my inducer at that point. So we can find my inducer motor on the wiring diagram. Here it is right here. Okay, if we look at the wiring diagram, it has my inducer neutral right here, and I have my inducer low speed right here. So we know that if all my switches are closed, it should be sending power out to my inducer. So I can now take my meter, put it across these 2 terminals, either at the board where we have wiring designations, or at the inducer motor. Okay, so if I didn't know, for example, that my white was neutral and my red was my low speed, I could go to this diagram, see it there. Or if you are like several of my coworkers and are completely colorblind, you can look for the wire numbers at both ends and check for voltage. Okay, so there's something for everybody here. So we know that at this point we should be sending line voltage to that inducer motor, and if it's coming out of the board and arriving at the inducer motor, that inducer motor should be running. If it's not, we know that we might have a trouble with the inducer motor. We can then power it down and ohm out the winding on the inducer motor just to confirm that that motor is dead. Okay, so we use the knowledge of sequence of operation in combination with the tools that are built into the wiring diagrams, guys, to trace power. And that's really the name of the game with electrical diagnostics, guys, is knowing how to trace power. You know, government corruption, they look for the money. In HVAC, we look for the power. Okay. If we can find our power, we can find where it's breaking down. Okay. If we were to come up to these limits and we tested up here, crossed 1 and 2 on 58 and 59 yellow, and we noticed that we had a voltage drop between those two things, now we know that one of these things is open. So we can leave a meter probe in 48 and then go out and just follow the numbers. So we could go 48 to 48, and we should have 0 volts there. If the flame rollout is closed, we should have 0 volts at 50. We should have 0 volts where 50 goes into the second flame rollout. And we should have 0 volts when it comes out of flame rollout 2 as well. Okay. And we should technically have 0 volts through all of this stuff. But if we come to one of these devices, say we get to thermal limit here, and we have wire 49 to wire 48 at this point, says that we have a voltage drop, and we're reading 24 volts between 48 and 49, and we weren't reading any voltage drop up to 51, we know that my power is being broken across this thermal limit. We can confirm that simply by taking the meter probe out of 48 and going from yellow 49 to yellow 51. That confirms that our thermal limit is open. If it shouldn't be, we know we've got a bad thermal limit, okay? But it's all about chasing power, guys. When we do the big Mitsubishi frequency-driven units that are really complicated, all it really breaks down to is chase the power through the system, okay? So use your knowledge of how switches should work and motors should work and solenoids and all that stuff that we've given you tonight, guys, and chase the power through the wiring diagram. The modern wiring diagrams are really great. They give you lots of information. I really like that stuff is both color-coded and numbered now. It makes it a lot easier. Any questions, guys, about anything we covered tonight?
I just have a question about a motor I was looking at the other day. It was a ECM motor, so it had 3-phase, so it just tested for ohms.
Mm-hmm.
And between, let's just say it was red, blue, and black. So between red and blue is getting like 4.6 ohms. And then I would switch it between red and another, the other end, like, I forget what I even said, but black. And it would bounce around. It wouldn't set at 4.6. It would go to 4.6, 3, 2, back up to 4.6 to 4.8 to 5. And it was really weird. I didn't know why it was doing that, or if it was, I kind of was thinking it was my meter, but then I'd stick it on my meter and it would be, you know, on the one, it would stay at 4.6 and not bounce around. So I was confused.
So that could actually be an indication of a bad connection. If you're seeing that bounce around on one lead versus not the other. So I've got that ECM motor right here. So this is a 3-phase motor. So I can throw my leads in here. And like you said, I should get equal resistance across all of these. So it should be fairly stable, assuming I get the leads on there right. Okay, so there's 12.2. And you can see as I flex my fingers around here, it changes the quality of my connection. So that's one component of it. Okay, but if you're able to get a good solid connection on two of those combinations, and one of them just doesn't work, it's probably a bad connection inside the motor. So we'll switch leads here. So there's that 12.5, fairly stable once I stop moving.
Your screen's still just on the wire diagram.
Oh, I'm sorry. I thought I stopped that. There we go. Okay, so if I hold really still, my number's fairly stable. Little fluctuations of a tenth I'm not worried about. But you'll notice if I get loose here and I start moving my probes around, okay, I'm still on that pad. But as I move it around, my number goes all over the place. Okay. So
Yeah, that was kind of, I sat there for a while and tried to make sure I was getting good connection on it, but it was bouncing quite a bit. So I bet you that wire connection in between there was, kind of off and on.
yeah. So you can have loose connections inside the motor. If you look down inside this motor, right, see if I can get an angle on it here. Right down here is where those connections will fail. A little tough to see, but there's a little staked on connector right there at the tip of my probe where those wires come in. And they're tied to the motor. That's where motor connections fail,
Oh,
is
yes.
that connection. So that can get loose. The other thing that a lot of guys neglect is their tools, the electrical tools. And I am due for a new set of leads here, guys. You can see mine are pretty chewed up. I'm missing the tip off of my red one. This one's been used by my son, so it's got a bunch of arcs in it. Okay, that's the other thing I'd recommend, guys, is always make sure you've got a set of really nice, sharp probes. That will help you in your endeavors to get electrical connections. You guys have kind of struggled, watching me struggle to keep my leads on stuff. It's because my tips are chewed to pieces. Okay, they like to slip around and slip off because I don't actually have a tip on that one anymore, and that one's bent and arced on. So if your leads are in bad shape, something that will help you get good electrical readings is simply replace your leads, guys. Get good quality leads. Hardened tips go a long way. So, but yeah, loose connections will give you those fluctuating voltages up and down. What else, guys? Other questions? Yeah, Keith's pointing out something. If you're ohming stuff out, guys, don't hold the leads on with your fingers like this, because if I do that, I'm reading the resistance through my hand. Okay. If I grab one lead in one hand and one lead in the other hand, you'll get mega ohms through your own body. So learn to use your meters with one hand. That saves you a lot of trouble. Also keeps you from getting shocked a lot.
Yeah, I was asking if you can do that to check for voltage.
Yep, absolutely. And that's where having sharp probes really comes in handy when you're checking for voltage. You don't want to have both of your pieces of equipment, both of your hands in a piece of live equipment. So learn to use your meter leads like chopsticks. Okay, so that you can get in there. The other thing that will help you a lot with meter leads is get alligator clip tips for your leads, or get leads that are just the little clips that go out and attach really firmly. So you can park one lead somewhere in the electrical circuit and then use your other lead to hopscotch around. Kind of fun little tricks. But spend a little money on your leads, make it worth it. What else you guys got? Okay. Well, I appreciate you guys taking time out of your evening to come to class and learn something. Thank you, Keith, for running the presentation for us tonight and helping us with all that. If you guys have any questions, feel free to hang around and ask. Otherwise, have a good evening. If you want a copy of the presentation, again, just shoot me an email like you did last time. I'm happy to send those out tomorrow to all you guys. Otherwise, thanks for coming, guys.
Yep, thank you. Appreciate it again.
Have a good night.
Thank you, guys.
Thank you. Thanks. Have a good night.